Voila, that should be fine. Okay, so let's go ahead and get started. So today, as much as we'd love to talk about all the technical things, this is not going to be a technical call. We'll be talking about the data science roadmap to a very in-depth degree, so that anyone who wants to get started in data science can understand what steps they need to take to start their journey in data science in that sort of regard. And I'll be able to break up this sort of session into the following aspects. So one will look at what exactly is data science, what are the pillars, and what's the life cycle, as well as the applications of data science. On the second layer, I'll be able to go in depth on the roadmap, and we'll talk about the following ones. So I've seen someone is in business intelligence, so data analysis will be very easy to understand exactly what you need. So that's going to be okay. However, beyond data analysis, so I'll talk about the roadmap for becoming a data analyst. We'll go deep into the roadmap for machine learning as well. And then we'll get to the advanced bit of data science, whether it's those of us who want to get into deep learning or AI, or those of us who want to explore big data engineering. And then finally, we'll talk about the next steps, where I'll be able to share more about Zindua School, the free foundational course, and how to get started with no strings attached whatsoever. So once again, we are so many in the call, so we cannot just let anyone unmute and ask a question like we usually do in smaller calls. So for this one, if you have a question, either raise your hand or drop it on the chat as well. And every once in a while, I'll be coming in to taking those questions. Okay, so there we go. Let us go ahead and get started. So I will go ahead and ask, just generally to get everyone engaged, what is data science? Anyone who has an idea of what data science is in general? Probably let me give it to Suki. I think you said you're in business intelligence. Yeah.
Hey, so just like a broad, I guess, definition from my point of view would be it's similar to data analysis.
Similar to data analysis. Now, how would you describe data analysis?
So analyzing lots of data.
Okay.
Analyzing partitioning it.
Okay. That is very correct. I'll go ahead and just use the same description there. So this is definitely a domain involving the complex analysis of data. So thank you for dropping that one, that sort of description. But I'll go ahead and say the reason why we have to do complex analysis of data. Now, data analysis tends to be not as broad as data science, because data science would involve machine learning to a degree, and we'll talk about the pillars of data science in a few. But in general sense, you're still analyzing or complex analysis of data. We're still analyzing data here. And we're doing this to, first of all, either find unseen patterns in data, to derive useful information from data, or three, we want to be able to make predictions or decisions out of this data in the first place. So that's what data science is. And to be able to understand this, let me use an example, for example. So a good example in the data science field, we'd go ahead to supermarkets or grocery stores, where if a grocery store starts analyzing the data, it sells data in regards to how cashiers, they service people, you're able to see what people are buying, and you're able to analyze the volumes of data there. Probably the one thing you can go ahead and discover there are unseen patterns, such as what goods are commonly bought together. So that's a very good example of it. And this allows this grocery store or supermarket to be able to optimize its shelf arrangement to optimize sales over there. So a good example is, we all know intuitively that when someone is buying milk, they're probably going to buy bread, right? Now, of course, there's other baskets of goods that are bought together. But when supermarkets analyze their sales data and see this kind of thing in regards to the cashier data they see for each and every single customer, so you do the complex analysis, then they can go ahead and say, because people usually buy this basket of items together, how about I put milk on the entrance and I put bread on the farthest corner ever? Because I know the person buying milk will probably buy bread as well. I want to optimize, or rather maximize, the amount of time they spend getting to the bread section so that they can make irrational buys in between. So there we're able to do the complex analysis of this sales data in a supermarket, find an unseen pattern, which could be either realizing that people buy milk and bread a lot, right? And we can be able now to design our supermarket to optimize our sales. And the way to optimize our sales is to improve or increase the number of irrational sales people make by increasing the time they spend looking at different goods in that market. Then let's go to example number two. Let's imagine I have a coffee shop, or rather I have, let's say, a number of coffee shops. Let's say it's a chain, right? So I'm Starbucks or Java, for those of you who are Kenyans here. And I start analyzing my sales data and I start deriving useful information about the different stores that I run. Some useful information would be when do we have sales spikes? So when are we getting the most orders as well? What sort of stores are doing better than the rest? So we're able to start pinpointing what locations have high demand, so that whenever we have a situation like COVID again, we know which sort of stores to maintain and which ones we can afford to do without, particularly when you're trying to go through a recession time. Or if we're trying to increase the number of sales we get or the number of stores we have, we know what areas or locations already have high demand that we can afford to throw in a second store or something. The other useful information would be when do we get the most sales, right? Probably it's usually between 5 to 7 p.m. Probably if probably we would want to increase the number of people available on a shift at that particular point. So you can see we're doing complex analysis to get this useful information. At times you go ahead and realize that on Mondays we have the lowest sales. So can we give people offers so that they start coming on Mondays to the coffee shop as well? So these are some of the different ways where you can start using data analysis to be able to derive useful information. And then the final one, which is highly aided by machine learning, is to be able to make predictions or decisions. So using our previous 10-year sales data, we can be able to make a prediction of how much sales we're going to make next month, thanks to machine learning algorithms that aid us in making these predictions pretty well, or time series analysis, which I'll talk about later on today as well in this sort of session. Okay, so that's just a general understanding of data science. So data science, the difference between data science and data analytics is data science would involve machine learning, which allows us to make these predictions way better and way more accurately. Okay, so let's understand the pillars of data science. So data science is comprised of three pillars in particular. The first and most important pillar is math and statistics. At the end of the day, when you're doing this analysis of data, we're using mathematical concepts and statistical methods to be able to derive insights from this data in the first place. So math and stats is a prerequisite for anyone trying to get into a data science career. And most of the time, it's very hard to learn math and statistics outside a typical college setup. So you'd see a lot of programs that are not necessarily in college or in a university setting. Try to make sure that you at least have that sort of math and stats prereq. Either you've done a STEM degree or you've done a good degree of math and stats to be able to take up data science. Because anyone can learn how to code, but learning math and stats be outside the university setup is not the easiest thing, though you can do it. Don't get me wrong off of it. And I'll talk about some of the mathematical and statistical concepts you do. However, what makes data science more valuable than typical data analysis is the fact that we are using our programming skills, and that's why computer science is a second pillar here. Why is this very important? It's because we are not confined to the abilities of a particular application, but you're able to code, rather. So we're able to program the sort of analysis processes that we'll be able to take up. We're able to start having machine learning algorithms based on code that can be able to give us predictions, which is not something you can do typically on an Excel sheet, which is what people use for analysis. So by learning computer science, we're getting a huge degree of customization. We're getting a huge degree of tools and solutions, particularly when you get to the machine learning layer and neural networks layer that are all coded in that allow us to make way more difficult predictions than what we could do in a typical Excel sheet in that sort of regard. So programming is a very fundamental pillar of data science, and it's what allows us to do even more complex analysis than what our typical tools can usually manage. If you do know both the math, statistics, and the computer science bit, then you're very apt in machine learning, right? And machine learning would usually just combine your mathematical skills and your programming skills and be able to build algorithms off of it to be able to either make these predictions. I'll talk about machine learning in the second phase of the roadmap. Okay. However, data science is useless if you do not have the domain expertise to be able to make use of data in a particular domain. So at the end of the day, we're not implementing data science in a silo, right? We're not just doing complex analysis without understanding what things you're analyzing. And that's why your domain expertise is essential. And it's the reason I was very deliberate in asking you what is your background whenever we were doing those sort of short intros. Because at the end of the day, we're analyzing data pegged to a particular domain. So a good example is I could be the best data scientist ever in life, no, right? But it's very difficult for me to make predictions in healthcare if I am not working with a healthcare professional or I do not have healthcare expertise. One, I do not understand how to structure the data. I do not understand the meaning of this data. I don't understand what is important, what is not important in when I'm trying to reduce the dimensions of the data or trying to create additional features of the data. I'll talk about most of these processes. So it just means like I could be so good at my machine learning layer, but if I don't have that domain knowledge, it's very hard for me to be able to make predictions in healthcare that are not flawed to a good degree as well. So your domain expertise is very, very essential. And this is what makes data science powerful, right? It makes it powerful because you can start applying these technical skills in a domain that you're already familiar with, whether you're coming from real estate, whether you're coming from business intelligence, whether you're a mechatronics engineer. I am just mentioning some of the different career pathways I've had some of you take. Awesome. So yes, so let me go ahead and summarize this pillar. If you know math and stats and you have domain expertise, that's what you usually see with traditional research that is done mostly in universities. So we're seeing very, very highly domain technical people being able to do traditional research with tools such as Stata, with tools such as Excel to be able to run experiments and be able to make conclusions off of it, right? Definitely the only reservation here is you're not able to apply the machine learning there to it. If you know both programming and you're well versed in a particular domain, doing product development or becoming a software developer is very, very easy. A good example is I could be someone very, very good at marketing. Probably I've done email marketing for the past 10 years myself. So I understand what works, what does not work. And I have some programming skills. I could be at the forefront of building tools for email automation or tools for affiliate management, all these things that involve that sort of marketing domain. Of course, it's either you have both, you have that domain expertise and programming skills, or you're working with someone with the domain expertise. I'll always stress that because you can always work with someone in that sort of regard. And then if you know math and stats, then you have machine learning. But if you have all the three pillars checked out, then you're on that sort of free flow domain we call data science, which is the amalgam of both three pillars, at least from the Venn diagram. Okay. So before I take in the first round of questions, let us talk about the typical life cycle of data science. And I'll use real estate as a good example over here. So data science works like a cycle. And this cycle starts from understanding the business or the problem we're trying to solve with this data. So a good example is someone comes to me and they say, I have data for real estate. I have data from a real estate company that contains features of houses and their prices for the past 20 years. And the problem understanding is most of the agents we have in our real estate company are finding it very difficult to identify the perfect price for a particular house. So what do we go ahead and say is, what can we do, or is there something we can do to find out based on the features of a house what is the ideal price for this particular house? So we do not have anything whatsoever apart from the data of features of houses for the past 20 years and their prices, and you're trying to figure out what will be the prices for this. Okay, and this is where your domain expertise is very, very essential. The first thing you'd understand here is having domain knowledge in real estate helps because you first of all know what type of features you need to care about. Is it the number of bedrooms? Is it the number of bathrooms? Is it how high the ceilings are? You'll be able to understand all the different parameters that people look at whenever they're trying to buy a house in the first place. And you'll start defining these are the data features that you need to be able to understand this problem to a good degree in that sort of regard. However, for someone like me who has no knowledge of real estate whatsoever, in off the top of my head, I just know bedrooms, bathrooms, size of the house, how high the ceilings are, does it have a parking space as the core things. I don't even know building materials, quality of the company that has built this, and all that. I don't have that. So as much as I can do this challenge by myself, there's a significant gap that's preventing me from optimizing the solution I can get off of this challenge in the first place. So domain knowledge is very applicable, particularly when you're defining that particular problem. And it's also going to be applicable in the next step when you're doing the data collection and sourcing. Right? With your domain knowledge, you'll know what type of data to collect, what to ignore, and even where to source them. Right? So someone like a chemist understands how to source data for a chemistry experiment, whereas someone who's not a chemist would not understand the procedure for that. So someone who already has chemistry knowledge is better suited to applying data science in chemistry for that sort of thing. So we understand the problem, we understand what data we need, and after that we start collecting that data or sourcing that data. There's different ways to source our data. Probably we already have a clear source. We have a CSV file, or we have a JSON file available that we can download to get this particular data. That's one option. Second thing is probably we have an API data access point. So probably I'm trying to analyze YouTube data. Because I don't have access to the YouTube database, I'll just go ahead and use their APIs to be able to get the segments of data that they make available through their APIs to do my YouTube analysis, for example. Or at times you have to go ahead and start collecting this data yourself, right? Either you're running experiments if it's one of those technical fields, or at times you're just trying to do a web scraper. So probably I want to go ahead and look at sales data from an e-commerce platform like Jumia or eBay. I can use my programming skills to design a web scraper that goes and automatically takes in data from that particular website and outputs a CSV file or a JSON file, which I can go ahead and do the analysis of. Now, in a typical Excel, or if you just know typical data analysis, this would be a difficult task if you don't have the programming when you think about it. But now that you're programmers and you can do that sort of sourcing, you can use your technical skills to be able to do advanced sourcing or more automated sourcing where you're not just copy pasting and you're able to create bigger databases because almost everything can be automated. Cool. Once we collect our data, or rather source our data, the next sort of layer would be data cleaning and preparation. This is whereby we start looking at our data and we see how we can clean it. So I have categorical data here. I know very well because I have a statistical background that my machine learning algorithms will not be able to read categorical data like that. Probably I need to encode this categorical data. Second thing is I'll go ahead and realize I have some missing values in certain columns. And using my domain knowledge, I'll be able to understand what I need to do to those columns. Should I drop those rows in the first place? Should I fill it with means? Should I fill it with medians? Or should I just forward fill or backward fill, right? Just make sure that they're in line with whatever row came in before them. Domain knowledge allows you to know what choice to make in this sort of regard. Based on my domain knowledge, I'll go ahead and identify whether outliers matter to my data or not. So there's a lot of cleaning procedures that you learn when you're doing data science, and most of them will be informed by your domain knowledge to a good degree, so that you apply your technical skills to at least clean your data to a good degree as well. So data cleaning, data preparation is very, very essential. I have put this in italics because it's special. Not every time do we do data maintenance or worry about the data architecture. However, for companies that are doing mass collection of data, mass automation of data collections, and they want to maintain an archive of data so that they can always reanalyze them and make their machine learning predictions better each and every single time, it is essential to start working on your data maintenance layer or your data architecture. So first, how can I do automated cleaning and preparation? How can I do automated data sourcing? How can I automate the data preparation after that? And once the data is prepared, how can I maintain it? Am I going to save it in a data lake, in a data warehouse, in a typical database, so that the next time our data analysts or our machine learning engineers want to access data to build a model, they can easily access that because everything has gone through this automated pipeline and is being maintained for constant access in the future. And whenever new data comes in, you're just able to add on to the already existing rows over there. So this is a very common thing that we see in really big companies. Think about YouTube, for example, where each and every single second someone's consuming in data, and they always need to make sure that the predictions of the videos are likely to like next time round you jump on YouTube is updated based on your interest in the past minute as well. So having a very clear data architecture is very important for a company like YouTube in that sort of regard. Okay, if you have questions, feel free to drop them on the chat as well. And data maintenance is something that you'll see some people do, some do not. For other people where we're not constantly collecting data, probably it's just a one-off experiment and then we'll go back with the cycle and collect data fresh, it's fine. But for companies that want to constantly improve their models, data maintenance is very important. I'll talk about that when I talk about data engineering in general. However, most of the time after cleaning, I usually go straight up to exploratory data analysis. Exploratory data analysis is where we start visualizing our data, we start understanding our data through graphs, through tables, and all this. We start doing summaries, what is the mean, median of all these sort of columns, all those sort of things you might have learned in descriptive statistics or graphing and all that. So we start doing all visualizations. And the thing about exploratory data analysis is it allows us to understand our data better, so that when we go to doing our machine learning models, we know what type of models work, which ones do not, or to allow us to understand our data better so that we can do better cleaning. So you'll see we always have a cycle between data cleaning, data preparation, and exploratory data analysis. And you always go through that cycle a couple of times up until you're done fully cleaning, you've done the full visualization, and you're comfortable to go to the next step. Okay. Now, once we do exploratory data analysis, we go back to cleaning, we explore the data again, we keep cleaning, we keep preparing. Then we are satisfied with the type of data we have and how clean it is. We can now go to the data modeling layer. And what happens in that data modeling layer? This is whereby we start using our machine learning algorithms to be able to make predictions off of the data. So the problem understanding we had in this life cycle was we have data for real estate for the past 20 years on the features of a house, right? So probably we had like 100 columns, all of them talking about different features of a house. And then we had one sort of dependent variable, which is the price of the house. Now, after cleaning my data and exploring my data and seeing the different prices, what was the average price and the likes, I can go to data modeling and looking at my data and I know my statistics, I can already see, because I'm trying to predict the price of a house, right, using its features, this is going to be a regression problem. Based on my exploratory data analysis, I can start figuring out what types of models would work well for this regression problem. If I could see my data was linearly separable, like most columns had some correlation with the price as well, I can easily use a simple linear regression. If I'm struggling with that, then I have to start thinking of using advanced regression algorithms such as random forest regression, right? So all these things are things you learn when you start getting to data science in that sort of regard to be able to make this prediction. Or probably I'll try all of them, and whichever gives me the best accuracy, I'll be able to start tuning it to be able to give me higher accuracy as well. But what I'm saying here is I understand it's continuous data, so I know it's going to be a regression algorithm that I'll be using, and I'm just trying to fit this regression algorithm using the data I have so that next time when I only have the features of the house, I can use that regression line to be able to predict the price of that particular house. Once again, if you have statistical knowledge, it's very easy to understand what I'm saying on regression. If you do not have, I'll highly advise you to start getting that as a prerequisite before getting to data science. However, modeling is useless if we're not doing model evaluation. And every time you model your data into a machine learning algorithm, you always want to do your model evaluation. And here, what will we be doing? We'll be trying to look at the accuracy of our model. So if I'm doing a classification problem, which is not what we have with house prices, I'll be looking at the accuracy score. So how many of the predictions were accurately predicted? So if my accuracy score is above 90%, that's good. So that's a good example of a model evaluation. If I'm doing a regression problem, then all of a sudden, what I'm trying to look at will be the mean squared error of my prediction. So all these are things we learn in statistics that you start applying in data science very, very well whenever you're working on machine learning. Okay. After that, I've also made this a red and in italics because not every time will we be doing model deployment. But when you're working for a company like, example, YouTube, most of the time, once you're able to build your model, you're able to fit it, you're able to evaluate it and make sure that it's accurate enough for you to keep making predictions. You want to deploy your model. In this case, YouTube would want to make sure that their model is integrated with their YouTube application so that they can make video recommendations to new users every time they reload the page. So that's a good example. Another example would be, let's say, Uber, right? Uber is going to deploy its model. So they've created models to be able to identify the closest vehicles to you or predict the price of your vehicle whenever you're making that particular order to high degree of accuracy, which also accounts for how much traffic you'd go through. So you can see that they analyze a lot of the traffic data as well as the distance data to be able to make that as well. But now for it to work in the Uber application, they have to deploy that model so that next time I go onto my Uber application, I request for a cab to take me from point A to point B, I have an accurate price estimate, and I have an accurate time estimate of how long I'm going to get there, and I'm able to get the closest driver to me in that sort of regard. So you deploy your models that can be live in normal applications. If you're talking about the house price prediction, probably we'll just have our own application in our real estate agency on how different individuals, even how the non-technical ones, will be able to key in the features of a house and get an output and price automatically because we've deployed our model. Once again, does not work always, but for certain layers, certain companies, certain industries, you'd want to deploy your model to make it available for use either by users or other people in the company. However, at the end of every sort of data science cycle, you always need to communicate your data. We're not working in a silo, we are working with other teams. So you need to be able to communicate your data. Communication is one of the most important skills in any industry out there. And data skills, whenever you're doing data science, it's even more important because You're supposed to draw insights off of this particular life cycle, off of this data, and they're supposed to communicate this insight to other people so that they can be able to make decisions or improve the process within a company. And thanks to your data communication, you generate the business insights. And based on those insights, we can be able to go back to step one. So let's say we do our house price prediction, we realize we are predicting price as well. But then we realize that for us to make a more accurate prediction, probably we should be collecting more of these features, or probably we need to collect the time that that sale was made. Probably that's something we realize that would have affected the price. And we go ahead and say that's one insight that could help us improve this algorithm beyond where we are at. So when we go ahead and define the business problem again, we'll be trying to identify the relationship between the time of a house sale and the price of that house, or probably add time as one of the columns or features in our data, so that we can be able to make an even better prediction in that sort of regard. So I'm just giving an example with real estate data, but this is a process we follow for each and every single data science project that we have out there. Okay, now let me relate this to careers. Most of the time, data scientists, we do pretty much everything in this particular data cycle, life cycle, if you're a data scientist. However, specialization is very key in the industry. So the blue areas are mostly done by data analysts. So they're the ones who do more of data cleaning and preparation, and then they'll do the exploratory data analysis, and then the data communication. However, when you start thinking about people who automate the data collection and sourcing, the people who build up the data architecture and the maintenance of data, and also deploy the model, then that's a specialized skill for data engineers. And then we also have machine learning engineers. They'll be more concerned about doing the data modeling and model evaluation, at times even the model deployment. So machine learning engineers will fall there. And then we'll have the general data scientists, and they'll do pretty much everything that I've bold. They should be versed in doing data collection, data cleaning, exploratory data analysis, data modeling, model evaluation, and the communication bit. That will be a general data scientist. And we, of course, have in certain industries where we have quants who are mostly in the financial industry, and they apply data science skills in that. And we can keep expanding this list, but I've talked about the 5 most common careers you see in data science based on the life cycle that I've been able to draw over here. What I always recommend for anyone starting to get into data science is what I call a T-shaped career. What does a T-shaped career? A T-shaped means, and you're talking about the flat layer of the letter T, be as general as possible in the entire life cycle. Make sure you understand the entire life cycle and you have technical skills to understand the entire, to do each and every single step in this particular life cycle. Once you're a generalist like that, and that's where we now get to the straight line of the T, you want to go in depth into one layer that matters or interests you the most. So I'd go ahead and suggest make sure you understand the entire data science life cycle, which is pretty much everything I've talked about over here. And once you're a general data scientist, choose which of the 3 that I've mentioned here, whether it's data analysis, data engineering, or machine learning, do you enjoy the most, and then start going more in depth and getting advanced in that particular skill. So if I'm a data analyst, now I want to be able to be very, very good at my data cleaning and preparation. I'm learning more and more tools other than the default tools that I'm going to give you today. If I want to be a data engineer, I want to go even deeper in understanding tools like Snowflake, being able to do cloud computing, full-on model deployment to become the best data engineer. So you want to be able to go even more in-depth than what a general data scientist would have. And that's what would make you as valuable as possible in the science career, where you want to be a generalist, so you won't get stuck at any point of the pipeline. However, you've specialized in something as soon as you're a generalist, and that's what we call the T-shaped career. Awesome. So with that, let me take in questions, and before we go to applications, and let me go straight up to the roadmap. Okay, any questions? So far, so good? Okay, Anna, it feels like you've dropped a plus sign there. If you have a question, feel free to raise your hand. But no questions so far, so good. So we can go ahead to the next layer. So now let's explore some of the applications of data science. Now, time is not on our side, so I'll try skim through this extremely fast. One of us was in business intelligence, so we can definitely use data science in business intelligence, where we use data that companies collect to be able to make business decisions to a good degree. This could be sales data. It could be any type of data based on your company. Let's say if you're running, let's say, a credit or education financing company like Chapter, for example, then our business intelligence involves being able to create the profiles of, let's say, the credit profiles of different individuals, being able to analyze them to see who's likely to default, who's not likely to default. right? We can start predicting how many repayments you're going to get based on default rates and the like. So business intelligence would be different from company to company, but anyone with a business degree understands that companies do make decisions from data to a good degree as well. Product development is one of the most common applications of data science, where we are seeing in advanced teams, like in some of these big tech companies, in each and every single feature product team, like product feature team. We have a data scientist who's trying to analyze the use of a particular feature and define how this could improve to achieve higher customer fulfillment or higher customer retention or higher customer engagement based on the type of application or product you're building in that sort of regard. So the stance for product development is extremely huge today, particularly in big tech companies where every product team would have a data scientist, whereas in smaller companies, you'd go ahead and see that you have a general data science team that's trying to make decisions for the company or a lot of functions of the company as a whole. But product development is a very important layer where data is being used a lot to define what sort of features we build in products. For those of you in marketing, we're seeing data science a lot in targeted marketing. I hope you guys can see my screen. It feels like it's not moving, so just apologies on that. Let me see that. I'll just change that. I hope you guys can see the targeted marketing just as a confirmation.
Okay. Yes, we can.
Awesome. Thank you very much. So targeted marketing. So think about how we're able to do advanced customer segmentations so that we can know which type of customer segment needs to receive this marketing message, which ones should not, which type of customer segment in my database is likely to respond well to my product more than others as well. We see this a lot in advertisement companies, or when you're launching your ads, you're trying to define your customer segments there. Facebook and Google will also do its advanced targeting based on users' interactions with their own tools in that sort of regard. Or even us, as we're doing our email marketing, we're trying to identify who are the people who are likely to attend this workshop more than the rest. So that we can target the invites and you don't have to spam each and every single person. Of course, we cannot do it to 100% accuracy, but at least that means that you spend more time with people who are likely to be more engaged with your content. So marketing analytics is a very important layer of data science. Data science is very important in targeted marketing or marketing analytics in general. Healthcare and medicine. We're now seeing a lot of healthcare professionals use machine learning to be able to make predictions. I think about people taking in X-ray data and looking at that X-ray data to see or predict whether someone has a benign or malignant tumor, whether someone has cancer. So they're trying to detect cancer very, very early in people using X-ray data. And this is after analyzing a lot of X-ray data from millions of patients in the past, that now machine learning algorithms can predict what doctors could not see in early stages because they're able to detect what the human eye could not see early on. Once again, he said complex analysis, we're able to see those sort of unseen patterns in data in that sort of regard. Sports and gaming, arguably one of my best examples out here, where we are seeing very big teams. For those of you who are into soccer or football, I'm personally an Arsenal fan, and I like that the Arsenal team has a very good scouting network that is data-based. So they're able to go into different countries and they're able to track different players by analyzing data of their movements when they're very, very young, and they start identifying talent of people who are likely to be very, very valuable talent in the future based on their movement on the pitch, how they respond to scenarios, whether it's a defender, like how they're able to approach these things. And this could be both video data of some of these games, as well as you guys have seen a lot of players these days have the beads, or rather they have trackers or they wear trackers to be able to track their game, their speed, and the likes as well. And this allows these teams to be able to make cheap purchases early on so that they can save money in the future and they do not have to buy players for $100 million plus. Betting companies are very, very renowned for using serious data science to be able to identify this particular odds and be able to optimize their sales or be able to predict the likelihood of a particular match so that they can be able to come up with the odds for a particular game, right? So that when you're betting, they know these are the perfect odds for betting, or this is the likelihood for these teams and the likes. For those of you who play fantasy football as well, if you've been losing for the longest while, like I've been losing for the longest while in the past 3 years, I got angry one day and I created a whole predictor. I used data science to look at data for the past 2 years to create an algorithm that is able to predict which players are likely to score the most points in my fantasy Premier League the next week. And I'm glad to say that now I'm on top of my small friends leagues just thanks to data science. Now, of course, that does not have monetary value to me, though I'm willing to bet on my position now. But even for fun, you can start doing more of the gaming aspects of your data science skills to a good degree. Cool. Transport, we've heard about driverless cars, where we're using AI to allow cars to be driverless in the first place. Or at times, we're just trying to effect traffic control, right? And we are able to use data science to understand when are we likely to have high traffic in a particular road, so that we can make sure the traffic lights are able to open up this road for a longer period than the rest. So, okay, I'm not a transport expert, but I think that's what they use the data to do, to be able to see how long the green light will last for a particular front, or even advise the government on what sort of roads need to be expanded, which ones, what sort of roads need to be expanded because of the traffic of people as well. Finance is highly renowned for data science, whether you're doing risk analysis, fraud detection. We know very well most central banks require all financial companies to detect fraud and not allow these particular transactions. But this is very hard for banks given the number of transactions they handle per second. How about you come up with a machine learning algorithm that's able to detect fraud such that we're able to flag those 1% transactions that are likely to be fraud, and then our compliance teams will be able to follow up on those sort of transactions rather than start wasting time for the 99% of transactions that are not likely to be fraud in the first place. Cool. And then we now start getting to advanced data science, borderline artificial intelligence here. Now we start working on things such as speech recognition, image recognition, natural language processing, and sentiment analysis. And I cannot talk about all the applications. I'm just mentioning some of the most common ones out there. And before we get to the roadmap, let me open it up for questions once again. Okay, thank you, Suki. Once again, there'll be a recording on the Slack channel. I'll go ahead and stress that again. I've seen Suki saying she has to leave, but I'll go ahead and drop this as well. So once again, I'll drop these links that I have over here. The first link is to join the free courses by Zindua School, whether you want to do data science or software development. Second one is to join the Slack channel where I'll be able to drop these slides, right, as well as the recording for this particular video. The third one is for those who want to apply to the core programs as well, which I'll talk about later on. Okay, let us go with fine speed to the next step, which is now the roadmap. I have lost my attendance data, so I don't know what I'm going to do here, but we'll see what we can do. Okay, so just a moment, just give me a minute as I switch back to the call. Just a minute. My apologies. I'm just leaving and then coming back into the call. Apologies. Okay, I am back. So let us go ahead with the roadmap. That is fine. Okay, I will go ahead and just click that button that I was missing before, and that should be good. Okay, thank you very much for waiting. Now let's get to the roadmap. So you want to get into data science, where should you get started in the first place? So the first layer for any aspiring data scientist is data analysis. So what do you need to do to become a data analyst in that regard? Make sure you can see my screen kindly. I think you can, and then we can go ahead smoothly. First one is you want to be able to learn a programming language. We said computer science is one of the really key pillars of data science. Python programming is by far the most popular programming language for people looking to do data science. An alternative is R, though I'll keep recommending Python programming because we run scrapers and we're able to see where the job demand is. And for data science, Python has far more tools than R, and it's far more demanding companies than R is in that sort of regard. However, in university setups, you'll see a lot of people still use R to a very good degree. The second layer is SQL programming. Now, first of all, SQL, structured query language, is a language that we use for querying databases in that sort of regard. And because most of our data is stored in databases, most of our data is stored in SQL or relational databases, it is very essential to be able to do analysis with SQL or to do analysis of data in an SQL-based database. Now, of course, you need to understand databases as a whole, And even as you do Python programming, you'll understand how to not only connect to SQL databases, but also connect to non-SQL databases. We call them NoSQL databases, which will be the JSON type of data, CSV data, and the like. So that's all fine as well. But because most of us, or most of our online transactions, or rather online data, is in SQL databases, data scientists do require this skill significantly. At times, you don't even need to bring in Python. You just do your queries and you're able to do analysis with SQL by itself. Cool. After that, we are now versed in Python. You're versed in SQL, right? Now we can start doing the advanced bit of Python data analysis. So what do we learn when you're doing Python data analysis? One, we need to learn how to source data with Python. So one, how can we use Python to access data through application programming interfaces, APIs? How can we use Python to script data from websites when you don't have access to APIs? And how can we use Python to be able to access data that's either in an SQL database or in a no SQL database? After that, we want to be able to do data analysis using the following two libraries that I'll recommend that you should learn. One will be NumPy arrays. We always want to do vectorized analysis. So NumPy is one of the very important libraries to learn when you're doing Python, when you're learning Python data analysis. Pandas allows us to transform Python or our Python environment into an Excel sheet. So this allows you to work with tabular data, and this is one of the most important libraries for data analysis or data cleaning. SciPy is definitely a bonus. I will always advise anyone after learning NumPy and Pandas to start getting some of their. I hope I'm not the one who left the call. I think it's me. If you can just remind me what I said last, if you don't mind, anyone. Okay. That's fine. I'll just continue. So we have Python data sourcing, and then I was on NumPy and Pandas as being the most important libraries for Python data analysis. SciPy is definitely a bonus. It definitely has some tools or resources or functionality that you don't necessarily find in Pandas or NumPy in the first place. So SciPy is a very important skill to get, particularly as you start getting deep into machine learning or higher level data analysis. Okay. After that, you want to be able to learn Python data visualization, where we learn about, we can do this using the following libraries: Matplotlib, Seaborn. Those are the common ones that I'd always advise someone to learn as well. We also have Plotly and Bokeh. However, I'm going to underline GeoPandas because GeoPandas is one of those special libraries that you can use to be able to do geo mapping of data as well. So when you start to have maps. Okay, I'm sorry I was muted. I hope you can hear me very well. Thank you very much, Anna, for raising this. So I'll skim through the Python data analysis again very, very fast. I've said the third step is Python data analysis, where we first of all learn Python data sourcing. So how do we use Python to get data from APIs? How do you use Python to script data from websites? And how do you use Python to access data from SQL or NoSQL databases? The second layer would be learning the two most important libraries for analysis. That will be NumPy and Pandas. And SciPy is one of the libraries I've said is a bonus, particularly as you get to advanced data analysis. The third layer of Python data analysis will be to do data visualization on Python. And here we'll use libraries such as Matplotlib, Seaborn. However, Plotly and Bokeh are good bonuses, but because we can't do geo-mapping visualization or map visualization on Matplotlib or Seaborn, GeoPandas is the library I'd recommend if you want to be able to do mapping of geographic data into maps, like mapping geographic data into maps. Yeah, there we go. After that, it is essential as a data analyst to not only confine yourself to Python or programming. Most of the time in companies, you already have access to data visualization tools that make your life easier. So it's essential that you learn either Power BI or Tableau or both, because you'll end up in a company that uses one of these tools and you don't want to overcomplicate your things if you can easily achieve it with a tool like Power BI, right? So Power BI is very common because it comes with Microsoft 365. So it's one of the tools that we recommend as a bonus for any data analyst out there. And the final one is because pretty much any company out there or any organization still uses Microsoft Excel to a good degree. You want to be able to be extremely vast with Microsoft Excel because most of the time you'll be getting your data in Excel. Most of the time you don't even need to go to Python and you can do your analysis to a good degree Likely there's no machine learning predictions on an Excel file in that sort of regard. So don't become the most technical data analyst who's very, very blank when it comes to Excel. Make sure you at least know this sort of basic skills, and then make sure that you have that sort of unique skill or technicality that allows you to even do more advanced analysis. Okay. Once we are data analysts and we've gone through most of those 5 steps, now we can now get to the second layer. First of all, once you learn the 5 steps I've talked about, you can easily get a data analyst job. You can even sit for the Google or IBM data analyst certification. So those are pretty much the most important skills. However, if you want to become a data scientist, then machine learning is very, very important. So what do we learn in machine learning? One, you need the following prerequisites, and I said math and statistics are very important. So for mathematics, you need to have a background, or you need to have fine knowledge of differential calculus. You need to be very good at linear algebra, and then having some knowledge of convex and concave optimization is something I'd always recommend for anyone. The most important will be differential calculus and linear algebra, because our machine learning algorithms will be using calculus and linear algebra. They're designed using those mathematical concepts. Second thing is machine learning is based off of statistical methods. So having a fine understanding of statistics is very, very important. So learn not only the descriptive and inferential statistics, but even probabilistic statistics, because some algorithms such as a naive Bayes classifier will be using some probabilistic statistical concepts such as Bayes' theorem for those of you who are into statistics already. So having a fine understanding of statistics is very, very essential to be able to get into machine learning and be able to understand how different algorithms work and be able to choose different algorithms for different problems. Okay, so now we start getting to the technical bit. So when you're learning machine learning, the first thing you should learn would be supervised learning. What is supervised learning? Supervised learning is the type of machine learning where you're trying to make prediction, but off of a training data set where you have both the features and the label. So a good example will be our house price regression problem that we had, whereby we have the features of a house and we have the prices of these different houses for the past 20 years. So we are trying to fit this data into a regression model so that it can detect the relationship between these features and the price, and we get a regression line so that the next time we only have features without the price, we can make a prediction. The most important thing about supervised learning is these algorithms depend on your data having both the features and the label. So the features are the columns, or rather the independent variables, and the label is the dependent variable, right? And it learns from that. And off of the lessons it gets from that, it can now make a prediction of the independent variable whenever you do not have the dependent variable. So it can make a dependent variable prediction off of the independent variables in the future, but it has to learn first of all from existing data. So what are the 2 most common types of algorithms here? We have classification, which is used to make categorical predictions. So probably we're trying to classify different drinks as whether they are beers or wines based on the features of this particular drink. Or regression, which works with continuous data, such as sales price, such as, let's say, the house prices that we've talked about a lot. Most of this, when we get to machine learning, we'll be applying this using the scikit-learn library, which is what I'd recommend when you're starting to learn machine learning anyway. Of course, TensorFlow can be used, but you always want to start with scikit-learn. It's a very, very easy tool to learn as you're starting machine learning. The second layer will now be the unsupervised learning. And what's the difference between unsupervised learning and supervised learning? In supervised learning, we have a training set that has both the features and the label that we use to train our algorithm so that the next time we don't have a label, we make a prediction. In unsupervised learning, we do not have labels whatsoever. We just have features. And so how does this work? Let me give an example. Good example is clustering. When you're clustering, we just have data of different customers. It could be a lot of data, different columns. However, there's no dependent variable in this sort of regard. So what unsupervised learning algorithms do, a good example is clustering, probably it will just try to find the similarities between these different customers and be able to segment our data to a really good degree. That's a good example of unsupervised learning in action. So we're not trying to make a prediction whatsoever, but it's able to look at the similarities of these different customers and be able to cluster them into clusters that we could send targeted marketing to. So clustering is a good example of an unsupervised learning algorithm. Second unsupervised learning algorithm that we use a lot in many projects will be dimensionality reduction. So what is dimensionality reduction? Dimensionality reduction is an algorithm that is able to analyze the different columns of a data set and determine how much each and every single column contributes to the explained variance of a data set. So you'd go ahead and realize that at times I have a very huge data set with 1,000 columns. However, 100 of these columns out of 1,000 explain 95% of the variance in this particular data. Running a regression algorithm with 1,000 columns is very, very cost intensive. It's very, very time intensive. It is not built, it is not going to perform fast. Like there's that sort of performance limitation. However, by learning, by doing a bit of dimensionality reduction on this particular data, that sort of regard, we're able to pinpoint the 100 columns that explain 95% of the variance of this data and reduce our columns from 1,000 to 100. Now, all of a sudden, we can easily fit a regression line faster and more efficiently and less costly, particularly when you're running it on a cloud platform. So that's another way where we start seeing the effects of unsupervised learning. If you have a question, feel free to drop it. Okay. Beyond those, we'll also be doing unsupervised learning with scikit-learn. But beyond those, you also want to be able to learn time series analysis with a library called stats model. Most of the data we collect today is time series data as well. So you also don't want to be off-tune with analyzing time series data, which is very, very hard to learn when you're getting started, but it's a very essential skill. Even when you're doing the prerequisites in math and stats, particularly when you're doing stats, it is nice to also learn some time series analysis statistics, those concepts such as ANOVA and the likes, so that when you're coming to implement them on stats models, you're not so blank about them. And then after that, it's essential to learn the model evaluation techniques for each and every single one of these algorithms that I've talked about, as well as how to deploy your model. Particularly here, I'll always advise deploying using Python, which is the language that you'd have learned if you've gotten here so far, so good. Okay. So before I take in question, let me now talk about the advanced concepts. So once you know data analysis and machine learning, you should be very, very vast. You should be a really good general data scientist. However, we can take your skills even further. And one way to take your skill even further is by learning big data engineering, where we start learning advanced skills for databases. We learn tools such as Apache Hadoop, Apache Spark, Apache Kafka, which allows us to now start automating our data pipelines to a good degree, be able to do data streaming with Apache Kafka and the likes. So all the things I had put in italics, right, in regards to data maintenance, when you start learning big data engineering, that starts to make sense to a lot of people. Keep in mind that while data science is a very common career today, or it's a very on-demand career, big data engineering is even more on demand. Because a lot of people learn data science, but at the end of the day, we need these data engineers to create data pipelines that allow data scientists to make predictions or access the data which they can analyze and make predictions off of. So it's a highly technical skill that a lot of people fear, but a technical skill that's extremely rewarding. It's the highest paid data career based off of our analysis. And I'll always recommend anyone, if you find it as an interest, it's a very lucrative career to get into and a very niche skill for a lot of people. Second thing is, if you enjoy machine learning a lot, you can expand into deep learning. Start learning about neural networks, start doing image recognition, speech recognition, and all these advanced AI things with libraries such as TensorFlow or PyTorch. So that's where we're starting to get into AI a bit. So here you learn things such as neural networks, right? You'll be able to do image classification and recognition, natural language processing, where we are starting to see computers understand the language. For example, my speech right now, I know even on Google Meet, I can always switch on the captions. So I can turn on captions. And now when I turn on captions on my screen, I can see it can understand my speech and write down exactly what I'm saying, so that those who can't hear me well can be able to see what I'm saying down there as well. So those are some of the AI sort of things we're able to achieve there. Sentiment analysis is by far the most common one that I see, where people are able to now start getting into social media. Let's say I'm a politician. I want to know how well I'm going to perform in the next election. So I go ahead and get Twitter data through their API, and I start gauging the sentiment. Are people saying positive or negative things about me, so I understand how much people love either my thoughts, myself, or a particular concept or idea, whichever it is, not just in politics, but in a lot of layers. Even when you're looking to understand the brand value of a company, some sentiment analysis would be really, really helpful when analyzing customer data or other what customers might have said about your brand on social media, for example. Then you have the really interesting ones like generative models. These are models that you start seeing they generate real life looking people who are fake, right? So they're able to look at images of millions of people, and then they can start outputting new faces that have never been seen before, but look extremely realistic, even voices in that sort of regard. And then you have reinforcement learning for those of us who want to get into robotics, where we are using rewards. So this is more game-based. We're using rewards and punishments to allow computers to learn and be able to achieve specific tasks in that sort of regard. Of course, these are very, very advanced technical things. Most of the time, people learn it when they're doing masters in data science, that sort of regard. But if this is something you're interested in, it's not content you're not going to get. It's not content we cover in the bootcamp, but it's content that you can always start exploring, read books, and watch more videos as soon as you're a data scientist to be able to jump onto some of these things as well. In any tech career, my biggest recommendation is you should always learn cloud computing. The three most common cloud platforms out there are AWS, Google Cloud, and Microsoft Azure. At the end of the day, most of our machine learning algorithms will be deployed on a cloud platform, and you need to be extremely vast on how to deploy this so that it can be used by other people. And cloud computing is a very underlooked skill, but a very important skill for data scientists in that sort of regard. I know in software development, it's widely accepted, but do not become a data scientist who does not know how to make your algorithms available or your models available to the general public. And that's it on the roadmap, at least in short. Let me see if there's any questions. Okay, thank you very much, Philip. I'll get to those questions in a few. But now let me first of all get to about Zindua School, and I'll answer that question on certifications as well. Okay. So as we talk about the next steps, what are the next steps? Definitely you want to get started in your data science journey. And one way to get started in your data science journey is you can go ahead and join Zindua School, which is a virtual part-time coding school that offers programs in both data science and web development. Zindua School is known, one, for personalized learning. So instead of being thrown in a class of 50 plus people, you get to work one-on-one with experts, expert technical mentors who will take you through the entire project or the entire program scope, right? So each and every single 5 weeks, you'll have a technical mentor assigned to you who will be working with you. That's the sort of relationship you want to be able to learn faster and to be able to learn based on what learning method works for you. Second thing is it is extremely project-based, and you'll be working on a daily challenge, a weekly project, and a capstone project. So you're definitely going to be graduating with a very, very loaded portfolio with data science skills, which is pretty much the curriculum will cover the pathway that I've talked about today anyway. So you'll have projects covering every bit of the pathway we've covered here. After that, you can go ahead and get industry certifications. And the industry certifications that you can seek after clearing the data science program will be the Microsoft Azure Data Science Associate Certification or the AWS Data Associate Certification as well. So all these are open certifications that you can seek. The curriculum is based off of this as soon as you graduate from that core data science program. However, what makes Zindua very, very interesting, and we as Chapter are glad to be working with Zindua School in that sort of regard, is one, you can either pay upfront or in installments, or you can defer up to 50% of your fees into an income share agreement where you learn now, just pay 50% and pay the rest as soon as you're earning as a percentage of your income. And for those of you who pay upfront or in installments, so those who are not in an income share agreement, there's also a 50% money back guarantee if you do not get a job 12 months after graduating the program. Because in an ISA, you pay nothing when you don't get a job, the money back guarantee also covers people who pay upfront. So the only caveat here is the income share agreement is only available to Kenyans at the moment. Hopefully it will be available to people in Ghana, South Africa, and Nigeria next year onwards. But for now, it's only Kenya. So that's the only thing that I can use, given that I see we have a very international attendance today. But if you're Kenyan and you already have a bachelor's degree or you're in a fourth year of university, then ISAs are an option to you. And that's just generally about Zindua School. However, we're not just here to go ahead and say that you need to get to the core program fast. Probably you need to explore. That's why we've made available that sort of Python for data science foundational course for free, which you can access when you go to that website, zinduaschool.thinkific.com. And once again, just to clear the call today, I will go ahead and share the links I had shared at the beginning of the call, right? And I'll drop them on the chat once again as I take questions. So if you want to join the free courses, I have dropped the link over there. I'll be sharing the video I've recorded here on Slack. So you need to join the Slack channel there, as well as the slides on Slack. And the final thing is you can go ahead and apply to join our core programs at Zindua School by clicking that apply button for those who want to go straight up to the core program. With that said, I'll open it up for any 1, 2, 3 questions from the audience, and then we can see how I can help more than what we've had we've talked about today. But Philip, I'm guessing I've answered your question.
Yes, thank you.
Thank you very much, Philip. Awesome. Any additional questions in regards to data science? Okay, there seems to be no question. Thank you very much, guys, for attending. Thank you for sticking till the end of this particular session. Once again, today is a sad day for me because this is the last data science info session that I'm doing personally. But this is something that Zindua School will keep doing again and again. And I have recorded this session, at least just to keep memories of the times I used to do the data science info session. And I hope this spoke value to you. And I hope that even that person who was a bit skeptical about data science, you've gotten the interest to be able to expand more into data science onwards. And I'm hoping I'll be able to see most of you in data science careers in the near future. Thank you very much for being a very, very interesting audience. And I hope you got the value and enjoy the rest of your night or the rest of your day based on wherever you are across the world.